Hello, everyone, and welcome to our talk on taking the WebAssembly compiler of WebKit. I'm Cao Zong, a security researcher and a master at the University of China's Academy of Sciences, and I'm joined by my collaborator, Wang Zheng. Together, we have a current interest in exploring and addressing vulnerabilities in modern web browsers. And today we will discuss our findings on the security issues in the WebKit, WebAssembly compiler, and how we address them using an innovation fast testing approach. Okay, here are the collaborators who have played an indispensable role in this work, and we could not have achieved our goals without everybody's valuable contributions. All right, let's begin by answering the question of why we choose a WebAssembly compiler and WebKit as a focus of our research. This question contains two key terms, and the first being WebAssembly compiler and the second being WebKit. Now focus on the first term, WebAssembly compiler. WebAssembly compiler is becoming increasingly popular as a high-performance compiler language that enables web apps to run more efficiently and securely. However, with its growing adoption, it's critical to ensure the security of the WebAssembly compiler since it directly impacts the overall security of web browsers and ultimately the web users. What's more, the WebAssembly 2.0 specification introduced several new features, which require the WebAssembly compiler to handle more code, and more code will bring more bugs, right? Okay, now let's talk about WebKit. As a widely used render engine in Apple software, WebKit comprises several critical components. One of those components is the WebAssembly compiler, and which is a part of the JavaScript engine. As we know, the JavaScript engine has been an important attack surface for web browsers in recent years, particularly in the JIT optimizer, where the code for achieving high efficiency is often complex and vulnerable in various optimization phases. However, the research for JavaScript engine should not only focus on vulnerability in the JIT compiler, but also the WebAssembly compiler. Yeah. With the introduction of the new WebAssembly 2.0 specification, WebKit team has significantly increased its investment in the WebAssembly compiler and released many new features. Simple statistics show that over the past 3 years, the number of the commit to the WebAssembly compiler has been increasing rapidly, surpassing those to the JIT compiler in 2022. Of course, this trend has also been noticed by other security researchers. In the Ponto in 2021, one of the vulnerabilities used to attack the Safari browsers was found in the WebAssembly compiler. Therefore, we believe it's necessary to conduct research on the WebAssembly compiler in WebKit. Okay. There are so many methods for bug hunting, but due to our interest in automatic method, we chose to use the fast testing techniques to find bugs in WebKit. Of course, there are also many approaches to fast testing, but the results are the ultimate goal. Next, I will introduce some of the tricky methods that we use. When it comes to fuzzy WebAssembly compiler, the most straightforward approach is to feed a bunch of WebAssembly samples into WebKit and see if it crashes. However, for a compiler, only samples that highly conform to the language specification can reach deep logic. Some samples with non-conforming format will be intercepted by the parser. Therefore, generating semi-well-formed samples is the main challenge for compiler fuzzing. After some investigation, we found that some work has already been done to solve this problem, such as WebAssembly Smith, WebAssembly compiler fuzzer within the V8 project, and the fuzzer in the binary project. However, after careful comparison, we found that the WebAssembly compiler fuzzer has the highest maintenance frequency and has discovered the most public known. Moreover, it continues to find new vulnerabilities in the V8 project now. Okay, this fuzzer is so interesting and good that we are eager to use it to the WebKit fuzzing, and this is also the inspiration of our work. We have studied the weight WebAssembly compile fuzzer and found that it can be logically divided into 3 parts. The first part is the libfuzzer framework, which is responsible for generating random data and collect coverage information and performing sample mutation. Okay, we only show the random data generating process in this job. The second part is a WebAssembly generator. In this part, the WebAssembly compile fuzzer cleverly converts random bytes of data into a highly structured WebAssembly module. Simply put, it uses random data as a control bytes to control every step of the WebAssembly generator's internal generation process. And the third part is a embedded weight used to compare and execute the WebAssembly module generated. Okay. Although those 3 parts can be logically spread, they are still tightly bound into code implementation. So how can we use this fuzzer for WebKit? We can certainly consider sharing the corpus, but that will separate the generator from sampling mutation, make the genetic algorithm effective. So we then consider directly embedding WebKit into this fuzzer by replacing the original weight back into WebKit backend for WebAssembly module compilation and execution, but we soon encountered some problems. For example, due to the complexity of the code, we might introduce vulnerabilities that should not exist during WebKit boarding. Additionally, integrating 2 different projects require a lot of development work, including jumping to different program interface and modify code to fit a new environment and so on. Those problems will increase time and cost of development. Moreover, if we want the fuzzer to adapt to the latest version of WebKit, we need to frequently synchronize this code. Those factors make the migration complex task. Then, what's the ideal solution? Of course, it's to test a complete WebKit application, which does not require repeated debugging of the embedded WebKit APIs, and code updating is also very convenient. And this is feasible because every purpose can also generate random data, collect coverage, and then mutation, just similar to libfuzzer. If we can reuse the WebAssembly generator in FI purpose, we can later modify the FI files to test the complete WebKit application. Right. Just as we are about to start doing this, we realize a problem. Yes, a problem again. Does the scenario of generation migration only exist between V8 and WebKit? Obviously not. If there is software that has a similar embedded fuzzer like with WebAssembly compiler, and there are peer applications that have the ability to accept input similar to that software, the generation migration method can be reused here. And therefore, we obtain this final graph and can summarize it as follows. By migrating the generator, we can enable some libfuzzers that were previously impossible to port to the peer application fuzzer. After all, the fuzzer ecosystem has developed for so many years, and countless libfuzzers contain a lot of expert knowledge, right? The expert knowledge. It is rather vast to be only used for a binding target, just one binding target, right? Okay, here are some examples of peer applications. First is the different JavaScript engines we just talked about. In addition to V8 and JavaScript core, there are other JavaScript engines such as SpiderMonkey and Chakra. And second, similar software libraries and frameworks. Many software libraries and frameworks have similar functionality, such as image processing, file processing a particular data format. And then there are different protocols implementations. Many network protocols have multiple different implementations. For example, there are many libraries and tools for handling HTTP request and response, or handling WebSocket connections. In those cases, a data generator may be reused across multiple implementations. Right, we have introduced our idea, and now let's take a look at the tool. The tool is completely open source, and its code is very concise and easy to use. We have also achieved a remarkable result using this tool, which we will introduce later. Let's take a look at how the FL++ extractor works. First, for a lib fuzzer that can be logically divided into a generator and a harness, the function LLVM fuzzer test1 input contain both parts, right? If that, we then manually patch the original fuzzer to remove harness function core. And then we apply the patch the FL++ extractor requires and use FLCC modified by the extractor project to compile libfuzzer with the original compilation command unchanged. This will build the libfuzzer into a shared library, which should have been an executable binary. Then we can use this shared library to further develop a custom mutator to work with FL++. In simple, right? Okay, we apply this workflow to await WebAssembly compile fuzzer and successfully compile it to a shared library with the same name, and name is just await WebAssembly compile fuzzer, but it's a shared library. Then, based on this shared library, we implemented a simple custom mutator library, and that wrapped the WebAssembly module in JavaScript. This way, FL++ can be directly applied to the fuzz testing process of WebKit, WebAssembly compiler. We also did some optimization work, such as adding persistent mode to WebKit and enabling shared memory fuzzing to further accelerate our testing, which improved our fuzz speed by more than 5 times. In addition, since the feature enabled by the WebAssembly compile fuzzer during sample generation were inconsistent with those enabled by default in WebKit, we also did some synchronization work on WebKit features in this fuzzer with different WebAssembly options of WebKit taken into account. All right. The results are very impressive. We run the fuzzer on the PC for less than 1 day and obtained so many crashes, although many of them are duplicates. So far, we have submitted a total of 13 security-related issues, and the fuzzer is still progressing for new crashes today, 4 of which have been assigned CVEs from Apple. Those issue affect Lint, BBQ, and OMG of the WebAssembly compiler WebKit. Okay, let's dive into some cases now.
Okay, thanks my partner Cao Zong for his sharing about fuzzing. My name is Wang Zheng, a security researcher in Tencent Security Xuanwu Lab. Moving on to the second part of the presentation, we will be more discussing some real-world security bugs found by the fuzzer mentioned before. This part will be more engaging as we will focus more on the issues themselves. This part mainly includes some basic knowledge, bug root cause analysis, and fix method. In general, there are 4 components in WebKit's WebAssembly, interpreter, and compiler. Lint is the interpreter, B3 and Air act like low-level optimizers that generate IR. BBQ is known for its fast compilation, while OMG is known for its fast code execution. The 3 vulnerabilities we are going to present today span across all compilation stages of WebAssembly. The interpreter of WebKit is Lint. It passes functions, generates assembly code, and ultimately executes them. In the example below, the add operator is first translated into lint code and then organized through instruction dispatch. Lint tracks execution count of functions and loops. When it reaches a certain threshold, it will lift up to the barbecue compiler. Barbecue is based on B3 air and air. It aims to compile the code as quickly as possible. It discards many optimization measures used in B3 and air. For instance, it employs a liner scan register and stack allocation algorithm, which is 11 times faster than the previous one. OMG, however, generates code that runs about twice as fast as barbecue. It utilizes more optimization measures to generate code, such as graph coloring register allocation algorithm. Okay, the first vulnerability we are going to discuss exists in the barbecue air compiler. It has an improper implementation of Stack Overflow error checks. This bug will ultimately lead to type confusion. Alright, let's take a look at the code snippet. This function generates the prologue part, which will be inserted into assembly code. Scratch here is a temporary register. It subtracts check size to get RSP register. If its memory address is lower than the stack limit, it indicates a stack overflow. At label 0, a comparison is performed, and if an overflow does occur, it jumps to the according function processing. This whole code will be linked into the original code. Okay, and at label 1, if we have a catch statement, we will load the address of instance pointer into Scratch and store the address on the call frame. Note that the owner of the instance has not been initialized at label 0, and this value will be used in the exception handling, which is unknown. Okay, let's see how to trigger this bug. Firstly, we must have an exception handler like catch or catch-all statement in WebAssembly code. Second, we must trigger a Stack Overflow bug in our WASM code. This will link the original code with overflow checking. WebKit traverses every call stack to find the corresponding cache stack to handle the exception. The following function visits every stack and fetches this object from call frame and casts it to a JS instance object. Since this object is not initialized, there is a dirty value in it. A type confusion bug happens. Okay, the fix is quite simple. We just place the code that stores on pointer in front of the Stack Overflow checking, ensuring that the value will be initialized before handling errors. And the second vulnerability is related to lint interpreter. The bug is caused by bad parsing of the delegate bytecode, which will break the stack balance and cause a stack overflow. Here we will introduce some basic knowledge and tech terms in WebAssembly. WebAssembly functions are highly structured functions. Each function body can be divided into blocks with some branching instructions. Each block can have its own signature, including parameter and return value information. WebKit uses 3 stack-like structures to assist with parsing. Each block corresponds to an expression stack. The control stack stores expression stacks in its parsing order, making it a stack of stacks. The enclosed expression stack stores expression stack temporarily when a new block is encountered. Okay, unreachable code is another principle. It means that the code that cannot be executed in reality, such as code that comes after a return statement and unconditional jump. Here is an example about delegate opcode. It's followed by a label number for error handling. If an exception occurs, this block uses label 0 for handling. It does not have its own code block, but only identifies which block is responsible for error handling. Okay, let's see some code in lint. If there is an reachable block in the function, we use the following function for parsing. It handles every opcode one by one. Here is the handler about the end tag in WebAssembly code. If there is only one unreachable block, this end label marks the end of the unreachable block scoop. At this time, the elements of the expression stack and the enclosed stack are swapped. Now let's turn our attention to the puzzling of the delegate. Delegate also marks the end of the current block. Observing this piece of code, we can see the logic of processing this bug is inconsistent with the end tag does. Firstly, the number of unreachable block is not reduced. From the perspective of lint, delegate does not really end the unreachable code block. The code comes after it is still unreachable. The second point is that the delegate should only process the expression stack when the number of unreachable code block becomes 1, because only then is the unreachable block truly ended, and we can start process a new expression stack. However, every time delegate is encountered, the return type is popped from the expression stack, eventually breaking the balance of stack. And about the poke, we place a delegate tag and a catch-all tag after the branch 0 tag. The branch opcode jumps to the label 0 conditionally. This makes the block behind it unreachable. The code then falls into the wrong branch. After that, when passing the catch-all tag, since the number of unreachable block has not been decreased, it incorrectly used the passUnreachable function instead of passExpression function. In normal cases, when passing the catch-all tag, a passJump instruction will be created. Like the picture on the right side, if there is no exception, this tag will be skipped directly. However, we will not emit such instruction with this bug because we believe that this is still unreachable block here. It jumps into the catch clause directly in the normal code, which will break the stack balance. Okay, the fix is borrowed from the logic of passing the end tag. It reduces the number of unreachable blocks each time, and processes the expression stack only if there is one unreachable block. Alright, the two bugs we mentioned just now affect a single compiler, and the last vulnerability affects both barbecue and OMG compilers. It will confuse WebKit to get a wrong error handler. First, let's talk something about call set index and stack map. In a WebAssembly program, each function has a unique function index used to identify the function. The call set index allows the program to locate the position of an exception. As for the stack map, it records information about the stack before and after function calls. It's used to restore the stock state during exception handling. The following function is used to generate exception handlers for function call points. At label 1, it checks if the function call points is wrapped in a try-catch block. If it's not, it returns to the caller function directly. Otherwise, at label 2, a handle object containing the call set index is generated. So imagine that if we make an invocation out of a try-catch block, we won't get such an object. So this is an initialization vulnerability. Barbecue and OMG use this method to generate optimized code. The stack map saves the call points and related variables. And for functions that are not in try-catch block, it will skip the storage process at label 3. So there will be no saved call set index on the const stack at label 4. As we have analyzed in the first bug, when error occurs, we visit all call stack to find handlers. During the process, the uninitialized value in call frame is obtained as exception handler index. If there is an error in the execution, we will build the entry buffer with the following function and obtain the stack map by passing callset index as the argument. Since we does not store the significant values in this object either, an assert about is triggered. Here is the fixed code. The patch is quite long. Here is the key code. It stores the callset index whenever function call exists. Okay, we are going to finish our talk and get some conclusions here. First, the tricky generator migration method works very well on new target like WebKit. Second, we use this efficient method to find multiple bugs in lint, barbecue, OMG, B3, and air. Some of them are still in process. Finally, the testing of WebAssembly compilers in WebKit is not enough, especially in WebAssembly 2.0 features. Okay, thank you for your precious time and attention. If you have any questions or comments, please feel free to ask. Thank you. Okay, since the time is running out, we can talk about it privately. And if you want to learn more about this topic, you can contact us on Twitter. Alright, thank you guys for attending our sharing. Hoping to see you again and have a good day. Thank you.